So our next speaker is already here, and we have just 1 minute to go. So without further ado, I'm going to welcome Vishrut Koh. He's a software development engineer at Grofers. Uh, hey Vishrut, hi.
Hi, how are you?
I'm good. How are you?
Pretty good.
All right. How excited are you for your talk?
I'm really excited.
Awesome. So I think you can just share your screen. He's going to talk to us. I think have you already shared your screen?
Yeah,
Uh, you have. Awesome. So he's going to talk to us about building production ready distributed task queue system with Celery. So I'm going to just add your screen. We can see it. Awesome. So you can just get started. I'm going to just get out. All the best.
thank you. So, all right. So, hi everyone. I am Vishrut Kohli. First of all, I would like to thank all of you for attending this talk, and I'm really excited to be here. So, I started working with Python, or should I say, fell in love with Python in my early days of college, and now I am using it as my primary tech stack at work, where we use it at tremendous scale. I am working as a software engineer at Grofers. If you do not know about Grofers, it is one of the most popular grocery e-commerce in India. If you want to chat about anything else or about this talk, you can reach me through my LinkedIn or through my personal portfolio. So, without further ado, let's dive into the good stuff. So, today we are going to see how to build a production ready distributed task queue management system with Celery. So, when I say production ready, I mean four things. It's highly efficient, it is scalable, it is transparent, and it is resilient. So, in this talk, we are going to cover what are task queues and why we need them, what is and why Celery, building a distributed task queuing system, tuning it to get maximum performance, adding resiliency or self healing capabilities to the system, what to do in times of SOS or emergencies, monitoring the system we built, and most importantly, bad jokes. So, I have tried to make this talk as descriptive as possible, but still, there are some prerequisites like some basic knowledge of Python, some basic knowledge of web development, worked or even heard about Celery before, and the most important one is a sense of humor and a love for chips. So, why task queues? So let's assume I own a mall and I want to keep track of how many people are entering in my mall. So I installed a small IoT sensor at my entrance, and whenever someone enters my mall, it shoots an API request to my web server. Then the request goes to the database and increments a counter. And at the end of the day, I can just check my database and see the count. This system was working pretty well for me, but one day I thought I'll stream a football match in my mall. So a lot of people came to the mall, and I was really excited to see the numbers in my database. But when I checked the database, the numbers I observed were relatively low, and I knew something was not right. So I investigated and figured out when a lot of people entered my mall, for each person, an API request was read to my web server, and there were a lot of concurrent requests trying to talk to the database. And due to the atomicity and locking at my database, many requests were timed out, and that's why the low count in the database. So there's got to be a better way. And there is. Task queues come to rescue. So let's see what are task queues. So if someone asked me this question when I was giving my university examinations, I would have answered task queue is a queue of tasks. And that is exactly what it is. I don't know why teachers don't like those answers, but yeah, it fits perfectly here. So now in the new architecture, whenever we get a request from my web server, instead of going and trying to increment the counter in the database, it puts it into the task queue and returns a 200 response. And now the DB can consume the request from the task queue at its own pace. So now we moved from a more real-time approach to a more eventually consistent type of approach. And that is okay for us because I only needed to see the DB at the end of the day. So what is and why Celery? So you must have heard a lot about task queues. There are a bunch of them available like Amazon SQS, Redis, Amazon MQ, RabbitMQ. But building a consumption and publishing mechanism for those task queues is not that straightforward. To help us with that, Celery gives us a plug and play task queue management framework, with which we can manage our task queues with ease. So in this talk, we are going to use some keywords. So let's just iterate over them once. We already know what task queues are from our previous example, but we'll just say it again. Task queues are queue of tasks. Then there is task. A task is the basic unit of work of a task queue. And a task queue can contain n number of tasks. Then here comes the worker. Worker is the basic unit of computation which lies outside your application and where a task is processed. Then in line, there is broker. So broker in layman language helps us with picking an offloaded task, putting it into the task queue, delivering the task to the worker from the task queue whenever the worker wants to process it. And the last one is result backend. So it is a highly available database which is used by Celery to keep track of all the tasks and their results, along with storing all kind of metadata for Celery. So some examples for result backend can be meme cache, Redis, etc. So okay, so before we start building the system, one question arises: which broker to choose? So there are a bunch of brokers available like RabbitMQ, Redis, etc. They all are great pieces of software, but works best for their own specific use cases. So for example, I'll cover the most common ones, RabbitMQ and Redis. So if you're looking for a highly efficient broker which supports several workers consuming from different queues and also offers some kind of persistence of task when it shuts down, then no doubt RabbitMQ is the way to go. But RabbitMQ is a little time consuming to set up and maintain. On the other hand, if you just want to use your broker as a quick messaging system, Redis is the way to go as it works really well for quick tasks and is very easy to set up too. Okay, so let's start building the system. So let's think of an e-commerce warehouse to build, and there are going to be three things which happen there: picking of the products, packing of the products, and delivery of the order. So the most basic kind of architecture for my warehouse would be something like this. I have one boy who picks up the products, packs the products, and delivers them. And this worked for me for some time, but now the orders are increasing, and I want to scale my operations. So I also employed a girl in the same warehouse. Now they both are parallelly picking, packing, and delivering the products. And this is fine as when more orders will start coming, I'll just add more people in the warehouse. But I think I can improve it a bit further as I know that these two people are really good at picking, but they are lousy at packing and they don't even have delivery bikes to deliver. So, what if we break this work into smaller fragments and get specialized people to do what they do best? So, now these two people are just doing the picking. I added an experienced packer who has its own packaging station and everything, and added people with delivery bikes to deliver more efficiently. So this way, we had one big task, we broke it into smaller fragments and executed them in order. And now in further slides, we will call this our pipeline. So why should we even use pipelines? There are a bunch of advantages we get while using pipelines. So let's go by them one by one. First, it gives you the ability to see bottlenecks and scale smaller components of the system instead of the whole system. So for example, so now if I see there are a lot of orders pending to be packed, so I can just add more people in the packing worker and scale the packing operations instead of scaling the whole pipeline like we did earlier. Second, this will give the ability to give different kind of machines to different tasks. So as per in our example, we can see the packing worker needs a packaging station, but a delivery worker needs a delivery bike. The same thing happens with the tech system. Different tasks need different kind of infrastructure. Some might need more CPU, some might need more memory. Third, it helps us keep track of statuses of tasks, which will add some kind of resiliency to the system by enabling retries at every step. So now, if a task fails, it will not retry from the beginning, but will get retried from the last checkpoint or last succeeded task in the pipeline. Okay, so now let's assume we have a sale going on and we have a lot of orders pouring in. Our warehouse is already full and we can't even add more people to the warehouse. So we got two ways here. First thing is we can buy a bigger warehouse, move all the the operations to the bigger warehouse and add more people in it. In tech terms, we call it vertical scaling. On the other hand, we can purchase a makeshift warehouse of the same size, add more people there, and run these two warehouses in parallel whilst the operations inside them are concurrent. In tech terms, we call it horizontal scaling. In my case, horizontal scaling makes more sense as the number of orders are variable, and after the sale ends, one warehouse would be able to cater all the orders alone. So, the code for our application would look something like this. We have an order receiver API which receives an order and offload it to the picking worker, which is the entry point in our pipeline. And the code for our pipeline is something like this. It starts with the picking worker, which picks up stuff from the aisle, passes it to the packing worker. The packing worker packs the stuff and passes it to the delivery worker. And in the last, the delivery worker delivers the stuff in time and makes the customer happy. So now we have built our celery system, but we don't know how well it performs. So, first things first, it's always better to benchmark before moving to any optimization. Because in my experience, I have seen if we go by intuition, either we end up over optimizing the system or optimizing wrong parts of the architecture. So, for example, in our pipeline, when I ran a load test, I saw the number of tasks queued at the picking worker were much higher than any other worker. So I knew from where I have to start optimizing. So let's ask ourselves one question. Can we use batching? So let's assume what happens in the picking task. Here in the picking task, a person is assigned an order, it goes to the aisle, picks up that order, and passes it to the packing worker. Now assume you have a lot of orders coming in, and to cater them, you added a lot of people in the picking worker, and everyone is trying to get something from the aisle. As lots of people are crowding the aisle, there will be some kind of wait time for everyone to pick their order. The exact same thing happens in our concurrent systems. The aisle acts as our database, and people act as our concurrent threads. To solve this problem, we can introduce patching. So instead of one person picking up just one order, we can make one person pick up 10 orders or even more. This way, we are decreasing our trips to the aisle by 10 times. But as we know, every good thing also comes with a trade-off. So now your retries and failures also happen at batch level. So if the ninth order failed for some reason in a batch of 10, still the whole batch of 10 will be retried. So if you're okay with this trade-off, then this can definitely decrease the load at your DB and give some kind of performance boost. So there is not much change in the code for our application, but instead of offloading it to the picking worker like before, we will offload it to the order aggregator worker. And the pipeline is also pretty much the same, just one more task named order aggregator is added, which contains the order chunking logic. And instead of passing just one order to the picking worker, it passes a chunk of orders to the picking worker. So the next optimization would be uh, always split tasks into IO bound and CPU bound tasks. So IO bound tasks are tasks in which a thread blocks the CPU and waits until an input or output is received. This makes the CPU unusable for the time it's just waiting. These kinds of tasks can be optimized with the help of Gevent or eventlet pools, which help us enable a non-blocking IO approach in which the thread goes to the CPU, registers its request, but does not block the CPU, and whenever its input or output is ready, the CPU raises a callback and the thread goes and collects it. This way, our CPU is never blocked by concurrent IO processes. On the other hand, a CPU bound task is a task which uses the CPU for crunching numbers or doing other CPU intensive tasks. For these kinds of tasks, we should use a pre-fork pool as it is based on Python's multiprocessing module and helps running parallel processes on multiple cores. And it's very easy to set up too. You just need to pass the pool name and the desired concurrency needed in the following command, and you will spin up a worker with the provided configuration in no time. Okay, use O-fare optimization when possible. So this is quite interesting. So the default approach Celery uses is the round robin approach to distribute tasks among distributed systems. So if you have a set of tasks that take varying amount of time to complete, either deliberately or due to some unpredictable network conditions, this will cause unexpected delays in total execution time for tasks in the queue, as you might end up having some tasks queued at some worker whilst some workers are idle. To solve this problem, we can use O-fare optimization, which distributes tasks according to the availability of workers instead of the number of workers available. So this option comes with a coordination cost penalty, but results in a much more predictable behavior if your tasks have varying execution times, as most IO-bound tasks will. So keeping track of results only if you need them. So as I told you about result backend, which stores all the metadata, statuses, and results of Celery, if you know you're not going to use them anywhere in your application, you can decrease the amount of network calls to your highly available database, and it can give you some amount of optimization. So now we will see how to add some kind of resiliency or self-healing capability to the system. So I think we all agree what Sentry.io's tagline is: software errors are inevitable, but chaos is not. So the most basic version of resiliency is to enable auto retries in times of failures. And you can add circuit breaking element. For example, uh, I have added 5 as the max number of retries. And if a task is retried 5 times and still failed, it will be ignored. To make it more resilient, we can add exponential backoff. So, for example, your task is dependent on another service, and that service is down. And let's assume the time between consecutive retries is 10 seconds. So, if the service is down and my first retry will happen at 10 seconds, the second one at 20 seconds, the third one at 30 seconds, the fourth one at 40 seconds, and the last one at 50 seconds. So, in this case, I gave 50 seconds breathing time to the other service to come back up so that I don't lose my task. So, to increase the amount of breathing time, we can use exponential backoff, which means the first retry will happen at 10 seconds, the second one at 20 seconds, the third one at 40 seconds, the fourth one at 80 seconds, and the last one at 160 seconds. So now the breathing time is increased from 50 seconds to 160 seconds. And if you want more breathing time, you can change the exponential backoff. Uh, the next one is acts late is equal to true. This means late acknowledgement. So by default, a broker marks a task as acknowledged when it delivers it to the worker. But if our worker goes down and restart, it loses that task. So to make the task resilient towards worker failures or infrastructure failures, we can use acts late is equal to true, which means until and unless the tasks is processed by the worker, it will not be marked acknowledged. So even if the worker goes down, the broker delivers the same task to it as it was still stored in the broker and was unacknowledged. And the last argument is retry jitter is equal to true. This param is used to add some kind of randomness to the system. So let's assume we have a concurrent system and there are chances two tasks are trying to access the same database resource. When they execute, they will form a deadlock and fail. We have our automatic retries enabled. So they'll get retried at the same time again, form a deadlock, and fail again, and this will repeat till the circuit breaks. In situations like these, we would want some kind of randomness to the retries so that they do not get retried again and again at the same time, and that is why retry jitter is helpful. And if you want to keep track of all your circuit break failures, you can use a DL queue or a dead little queue to store your failed tasks. Okay, so when your system is down, the first thing you should do is check your CPU and memory utilization. If your CPU utilization is high, then horizontally or vertically scaling according to your infrastructure could help. But if your memory utilization is high and you know for a fact that your code is not using that kind of memory, there are chances there is some memory leak in your code. I know what you're thinking. You might be wondering, memory leak in Python? That is impossible. And I am with you. If you're working with core Python, that is impossible. But when many of the libraries you are using are built with C Python or anything else, there are chances there is some kind of memory leak happening under the hood, which is not in your hands. So, to solve that problem, Celery provides two thresholds: max memory per child and max tasks per child. So, with the help of these commands, you can set thresholds either on number of tasks executed by the process or the amount of memory being used by the process. And when any of the thresholds is reached, it rotates the process and clears out stagnant memory. So, when you're running something in production, you should always have the capability to keep an eye on it. And Flower works really well with just running one command. You can set up a full-fledged monitoring tool for your Celery setup. So it gives you capabilities like purging queues, view acknowledgement rates, view and modify queue worker instances, view scheduled tasks. It has an HTTP API for almost every data point so that you can integrate it in your own monitoring dashboards as well. And also, you can use those endpoints to configure alerts so that you know when your system is going down beforehand. And if you are using RabbitMQ as your broker and you're more comfortable with RabbitMQ instead of Flower, then you can use RabbitMQ admin panel to monitor your system at the broker level itself. So it also gives features such as purging, deleting, and monitoring queues. So to conclude, in this talk, we understood why pipelines are better, how to tune your Celery config to get maximum performance, uh, how to add your setup, how to make your setup resilient or self-healing, uh, how to do how what to do when unknown things are hogging up on memory resources, and how to keep an eye on your system. So if we follow all these steps while building our system, we will be facing a lot less issues. Our system will be production ready and we will sleep soundly. So that is it from me. If you have any questions or feedback, I'd be happy to work on it. Also, if you didn't like the presentation, I'm also open to take virtual tomatoes. So yeah, that is it from me. Over to you, Sangarshana.
Hey, thank you for that talk. It was amazing. I don't think you would be getting any tomatoes though. And
I
so you
hope so.
can, yeah, you won't, I'm sure. Uh, I don't think we have any questions on YouTube. I think it's mostly because it's like an odd time for people around the world. So like
I understand
either
that.
most of them are sleeping or they're like yeah. So also you can actually hang around on Discord or on the YouTube chat. Someone might pop up a question. So I think he'll be hang out there if you guys want to ask any questions regarding to Celery, task queues, anything else you saw his talk, you can just ask it out. Thank you so much for your talk. It was amazing.
All right. Hey, thank you. Thank you for having me. Bye bye.
All right. So think our next talk is scheduled to start at 12. So I think we have around 8 minutes left before the start of our second talk. So I think now it's the time to play a sponsor video, I guess. Let me just find it and play it for you guys.